So today we're starting our chapter on representation theory. Some of this at the start here might be review. I didn't get a chance to filter it as well as I normally would. Screen it. The first topic here in this is weights and maximal vectors, which I think this will largely be reviewed, but there was a couple things in here that seemed new, so hoping we'll get some new stuff out of this. And first topic is weight spaces. If V is a finite dimensional L module, L is our semi-simple Lie algebra with a Cartan subalgebra H, root system phi, base delta, Weyl group W, all that fun stuff. Then we saw in a previous theorem that H, our Cartan subalgebra of L, acts diagonally on V. So V is the combination of V, union of V lambdas, lambda in H star, and for just a reminder, V lambda is a set of V and V, the eigenvectors in V of H, whose action on by H is given by a character function, by the character function of our lambda. For arbitrary V, the subspaces V prime are still well defined, lambda. Whenever V lambda is non-zero, we call it a weight space. And we call lambda a weight of H on V. Well, looking at examples. Example. Viewing our semi-simple Lie algebra as an L module via the adjoint, we see that the weights are our roots and with which have weight space, of course. L alpha of dimension 1 and 0, which is a weight space of our H of dimension of the, I believe that's the number of elements in our base, yeah. I guess there are two examples here. when L is SL2 of F, the linear function lambda on H is determined by its value at the basis vector H. So this is just a reminder, because we've done that kind of analysis before, and it's just like tying that back to this idea of weights. Now, in the infinite dimensional case, V may not be the sum of its weight spaces. But the sum V prime of its weight spaces is always direct. Which is just like showing the eigenvectors of distinct eigenvalues of a given linear transformation are linearly independent. Also, V prime is an L submodule of V as L alpha for alpha and alpha permeates the weight spaces. Namely, if we have X from L alpha, V from X is from a weight space of alpha, V is from the weight space of lambda, and H is an H, then H acting on X acting on V is equal to X acting on H acting on V plus the bracket of H on X acting on V, which is going to be lambda H plus alpha H of X on V, so that L alpha sends V lambda to the weight space of lambda plus alpha, which we're going to rewrite this all as a lemma here. Part A is literally just what I just said. The weight space of the root alpha maps the weight space of a weight lambda into the weight space of their sum. Part B V prime is the sum over lambda and H star of V lambda is a direct sum with V prime an L submodule of V. And part C, if the dimension of V is finite, then V is V prime. Next chapter is standard cyclic modules. So by definition, if you recall, a maximal vector of weight lambda in an L module V, I guess I'd write that out, in an L module V is a non-zero vector V plus in in V lambda killed by all L alpha for alpha inner base. If L is simple, for example, and beta is the maximal root in phi relative to delta, then any non-zero element of L beta is a maximal vector for the adjoint representation of L. And this is obviously the only possible maximal vector in this case. When we are in infinite dimensions, we cannot guarantee maximal vectors. Maximal vectors, as you can always just keep going higher, I think is the idea here. However, when the dimension of V is finite, then the Borel subalgebra B delta is H plus the sum over the positive roots of the L alpha has a common eigenvector by Lee's theorem. And this is maximal. All right. In order to study finite dimensional irreducible L modules, it's useful to first study the larger class of L modules generated by a maximal vector. if V is UL on V plus for a maximal vector V plus of weight lambda, we say that V is standard cyclic and lambda is of course the highest weight. Of V. And we can go ahead and describe the structure of such a module. So we're going to fix a non-zero x alpha in L alpha. And choose, of course, y alpha in L negative alpha such that the bracket of x alpha and y alpha is h alpha, as you would expect. Recall the partial ordering of lambda being greater than mu if and only if lambda minus mu is a sum of positive roots. Alright. We have a theorem with a lot of parts. Let V be a standard cyclic L module with maximal vector V plus in V lambda. Let V plus be the collection of beta I from 1 to m. Alright, then part A. V is spanned by the vectors of vi1 beta 1 through vim beta m acting on V plus, for ij being positive integers, with V being the direct sum of its weight spaces. Part B, that the weights of V are of the form mu equals lambda minus the sum ki alpha I for ki being positive integers, that is always are satisfied being less than our maximal weight lambda. Part C, for each mu in H star, the dimension of V mu is finite, and the dimension of V lambda is 1. part D, I told you this is going to keep going. Each submodule of V, is the direct sum of its weight spaces. Part E, V is an indecomposable L module with unique maximal submodule and corresponding unique irreducible quotient F is at every non-zero homomorphic image of V is also standard cyclic of weight lambda. And the proof of this, we're finally done presenting this theorem. First off, for part A, L is n minus plus B, where n minus is the union of L alpha for negative alpha, and B is the Borel subalgebra of our base. From the Poincare-Birkhoff-Witt theorem, we have that UL on V plus is U of n minus, one second. Yeah, I skipped over some instructions. So just to make it clear, that U that I'm writing, I'm pretty sure, I was assuming that's the universal. Yeah. Yeah, that's the universal of L. Because we skipped over that part because it was a duplicate and they just introduced their own notation because that's, of course, they did. So the universal of L on V plus is universal of n minus some universal of B on V plus, which is universal of n minus on F scaling up our copy of V plus, since V plus is a common eigenvector for B by definition. Now U of n minus has a basis of monomials yi1 beta 1 times through ym beta m, and that gives us part A. Alright, next up, the vector y times I1 beta 1 multiplied through y to the im over beta m, acting on a v plus, has a weight of lambda minus the sum of our ij beta j. Rewriting each beta j as a non-negative integer linear combination of simple roots we get done. We get b here. Only finite of such vectors. Finitely such vectors of the form of yi1, yb1 to the i1 through ybm to the im on v plus have the sum of ij bj equals a prescribed sum of ki alpha I. From part A, these span the weight space v mu for mu being lambda minus the sum of ki alpha I. The only such vector with weight mu equals lambda is v plus, which gives us part C. Alright. Now, for D, we're going to let W be a submodule of V with W and W as the sum of vectors Vi in V mu, each belonging to distinct weights. We must show that all Vi lie in W. If not, we can choose such W as the sum of Vi through V1 through Vn with n minimal and n greater than 1. And we see that no Vi belongs to W. We're going to find an H and H for which mu1H is not equal to mu2h. Then h on w is the sum for mu ih with vi. We could lie in w, as does h minus mu 1 of h on 1 acting on w, which is mu 2h minus mu 1h acting on v2 plus all the way through mu nh minus mu 1h acting on Vn, which is non-zero. With the choice of W, this is going to force V2 to be in W, which is not going to be possible, so that gives us that case D. And from these we see, from these last two results, we see each proper submodule of V lies in the sum of weight spaces other than V lambda so the sum of which we're going to call W of all such submodules is itself proper, thus V has a unique maximal, spelled unique wrong, unique maximal submodule and unique irreducible quotient. V also cannot be the direct sum of two proper submodules as each is contained in W. And that kind of rounds off our proof here with E and F coming immediately from that. Alright, and then there is a corollary which we're going to follow up here this with. That'll be into this section, and I'm wondering how long it's been. We'll see how long this takes. Alright. Let V as above. And suppose further V is an irreducible L module. Then our maximal vector V plus is the unique maximal vector in V up to, of course, scalar multiples. Come on, don't be beeping all the time. Proof. If W plus is a maximal vector, the maximal vector in the universal algebra of L on W plus is going to be V. Since our V is irreducible, I'm going to need a new page, I think. Yeah, we'll go for it. Irreducible. Then the above theorem applies to both our V plus and W plus. If our W plus has weight lambda prime, we know then that the weight of our other vector has to be less than our maximal vector W, weight of our maximal vector W plus, but the weight of our W plus has to be less than the weight of the maximal vector less than or equal to the weight of our maximal vector lambda. So lambda equals lambda prime. So by part C, we get that W plus is proportional to our V plus. And that'll be the end of this theorem, end of this section 2. And I'm hoping we can call the video there. I don't know how long the next section is going to be. I mean, it's... It is 1 unit, so, like, how long have we been here? 2... So I'll add on another, like, half to our video. Alright, that'll take it. We're at time here today, so I think we'll call it here. And then, next video we'll finish off our discussion here of weights and maximal vectors, and we'll move on to finite dimensional modules. So look forward to that, I guess.